Alright, the figure above shows a particle with positive charge plus q traveling with a constant speed v0 to the right and in the plane of the page. The particle is approaching a region shown by the dashed box that contains a constant uniform field, and the effects of gravity are negligible. Part A. Subpart 1. On the figure below, draw a possible path of the particle in the region if the region contains only electric field directed towards the bottom of the page. So let's put our electric field here. And remember, it's constant. So I guess we can show that by, right, that's our electric field. Once the particle has entered the electric field, in fact anywhere in the electric field, the particle is going to have a force which is the electric force, Q times the electric field. That's a constant force, so we have something which is getting a constant acceleration towards the bottom, which would be some sort of parabolic path, something like that. Subpart 2. On the figure below, draw a possible path of the particle in the region if the region contains only a magnetic field directed out of the page. So now our magnetic field is this. And when we reach the edge of the box with some velocity like this, well, we can do right-hand rule, and we can say that if we have, here are our axes, and we have our velocity is along this axis, and the magnetic field is along that axis, then the right-hand rule tells us that the motion, or sorry, the force, not the motion, but the force is downward. So here we get a downward force. So it deflects just like the other one, except that once we're in this region, since it was perpendicular, we've lost no speeds. Now we're going this way. And that would produce an inward force like this. And in fact, we know what ends up happening for real is a circular path. I guess in this case, a quarter circular path before it leaves at this point at the same speed. And I suppose to say, for the first part, we can go back and say it leaves like this at a greater speed. Oops, over at part 3. Subpart 3, for which of the previous situations is the motion more similar to that of a projectile in a gravitational field near the Earth's surface, and why? So what is the motion of a projectile in the Earth's gravitational field? Well, of course, it would be if we were to, say, fire something moving horizontally, it would take a path like this. A parabolic path, because we know that the force due to gravity would be like this. This is the electric field, so the E field is more similar because the force produced is constant. The magnetic field is less like that because its force is not constant. Although it has a constant strength, it changes its direction continuously. Part B. Another region of space contains an electric field directed towards the top of the page and a magnetic field directed out of the page. Both fields are constant and uniform. A horizontal beam of protons with a variety of speeds enters the region as shown above. Protons exit the region at a variety of locations, including points 1 and 2 as shown in the figure. In a coherent paragraph-length response, explain why some protons exit the region at point 1 and others exit at point 2. Use physics principles to explain your reasoning. 1. Have to just highlight how hilarious this is. I don't know what else you would use. We would say like magic pixie dust, but we want to use physics. Some other things to note. It's a beam of protons, so those are all the same. They all have the same charge. Q equals just the electric charge, but with a variety of speeds. So that's probably going to matter. Let's figure out the force. So if we take, we draw a free body diagram, we know that we're going to get an electric field pulling upward, and we're going to get a magnetic field force pulling downward. And we know this because, of course, the protons move in the direction of the electric field, or feel a force in the direction of the electric field, because they're positive. And we know that the electric force is just going to be QE. And they move in the same direction because the field tells you which way that, sorry, I should correct that. They feel a force, electric force, in the same direction because the electric field direction tells you the direction of the force felt by a positive particle. So, yay. And then for the magnetic field, we know that the force is going to be something like QVB, something like that. So let's take the case just as this is the case when we've just entered. So we have a proton here, and it's just come in with some initial speed. So it's heading that way. And we can see that the net force, let's take a coordinate frame which takes that as y and that as x. Then the net force in the y direction is Fe minus Fb, because they're opposed. So it's going to be something like QE minus QVB. And that, of course, equals m times the acceleration in the y direction. So the acceleration in the y direction is q over m, so-called charge to mass ratio, times E minus VB. And we see that these two numbers then contain the key, because what we'll have is that, let's take it like this. If we want the acceleration, say we decided we want the acceleration to be positive. So AY greater than 0 implies E minus VB greater than 0, which implies E is greater than VB, which implies that V is less than E over B. So if the particle is moving slowly, relatively slowly, a smaller value of this critical value, then it will deflect upward, at least at first. When it comes in, there'll be an upward acceleration. And so a low speed particle would do maybe something like this when V is less than E over B. On the other hand, if V is greater than E over B, it would do that. There's clearly a case in the middle where they could just be balanced and it could land there. Of course, my particles have missed, but that's because I picked particular values. There would be some V more than E over B, which would cause it to go through portal 2. And there's some V less than E over B that would go through portal 1. The relevant point here being that the magnetic force depends on the speed, so the balance between the electric and magnetic forces will depend on what speed the particle came in with. I haven't done the full-on thing. The direction of the magnetic force is going to change, but it's always going to be curving it away from the midline, all right, from curving it away from this line. The magnetic force always points away from that, so they're always going to curve up or down, and therefore some of them at least might go through 1 or 2.